Hello, Physics 2. All right, we are progressing through Chapter 23, moving on into light waves. So what we're going to do, so that you know what's coming, we're going to finish up the next couple sections, and then I actually move on to a PowerPoint lecture I think your book does an okay job of kind of doing all of these hodgepodge different topics relating to light, but I think there's some really straightforward ways of explaining it that I just prefer. So that's what you can expect, and then we'll get into Supplemental 3, which can be found for free online, and all of the odd answers are in the back of the textbook you have now. All right, so the light wave. If you accelerate a charge once, you get a pulse. And we have already analyzed pulses. If a charge is moved sinusoidally, you get continuous radiation. So, the position for this light wave radiation is described by y equals y max sine omega t. So you've seen equations like this before in this class. You saw the first one in Chapter 4 of Physics 1, and now you're seeing it again. I mean, at the end of the day, physics is all about waves. Waves, energy, and matter and interactions. So you keep seeing these oscillatory movements come back over and over and over again. All of this vibrating energy. All right, so as you recall, omega is angular frequency. And so couple of notes just to kind of get you thinking in the right frame of mind. We are very familiar with the spring model of matter. So we know we've got all of this vibrating matter around. And it also works, this idea, it works for electrons as well. And so regular matter emits extra radiation as sinusoidal electromagnetic radiation. So we can get the velocity in y, Vy is equal to dy dt, which is omega y max. So in this case, we're just plugging this equation in. We're taking the time-based derivative, omega y max, cosine omega t, and the acceleration in y, so dvy dt, or the second derivative of position, is equal to minus omega squared y max sine omega t. So for those of you who are in the calculus class, you should verify these equations. For those of you who are in the algebra-based class, you can verify them if you've taken calculus. If not, you can just accept the results and know where it comes from. So if the acceleration is in y, then the electromagnetic radiation is in all directions except y. So then the radiation would be in x and z. So, and we've already seen that when we've looked at those E fields and B fields. In terms of how they are perpendicular to each other with velocity perpendicular to that. So whatever the direction of motion is in, that is not the direction where the field is. Okay. So for waves in xz, then you would have the electric field in y is equal to 1 over 4 pi epsilon naught minus q ay c squared over r. So you'd have ey 1 over 4 pi epsilon naught q. Now we do have an expression for the acceleration in y. We did just derive it. Here it is. So there's nothing to stop us from just going ahead and subbing that in. And so it's going to have a minus sign. So we're going to have two minus signs. They'll cancel each other out. So you get omega squared y max sine of omega t c squared times r. And so now you have the expression combining everything we know. All right, so in order to talk more about waves, we need to just do some wave review. So we're going to look at the anatomy of a wave. So the next, really the rest of this chapter and then into supplemental 3, we really need to make sure that we understand waves. And so we've talked about them all year, but we're going to talk about them again because they're always important to go back to. So the anatomy of a wave. So here we have a wave. Okay, so this here is the amplitude. So that's the highest length. This is lambda, the wavelength, and then you could look at the time it takes to get from here to here. That is the period. And you can go after velocity, which is how fast this wave is propagating through time, space, matter. Depends on what type of wave it is. So we know that light waves move at the speed of light, but sound waves propagate through matter much, much slower than that. Okay, so the frequency of a wave is equal to 1 over the period. It has units of 1 over second or hertz. Frequency is also equal to angular frequency divided by 2 pi. And remember, period, the units for the period is time seconds. Moving on, wavelength. So wavelength we denote with a lowercase lambda, a Greek L. For a light wave, it's equal to the speed of light times the period, leaving you with a unit of meters, or c is equal to lambda times frequency. So then you would have meters over seconds. Both of those things work out from a unit analysis perspective. Always double check your unit analysis with stuff like this. The speed of propagation, that would be a v without a vector, is equal to lambda divided by t. V is also equal to d over delta t. So you might have the wavelength and the period, or you might have where the wave is first detected and then the time of a second detection. Both ways that you might use to calculate the speed of propagation. All right, so let's do an example. A red laser has a lambda of 800 nanometers. So this is actually a, let me try that again. A near infrared laser. I often choose this wavelength. It's near and dear to my heart. I worked with a kilohertz laser that had a wavelength of 800 nanometers. It was very faint and very, very, very destructive to your vision if you ever caught a glance of it in your eye. So, what is the frequency? I never caught a glance of it in my eye, but I really enjoyed working with lasers. So, the velocity is equal to, the speed is equal to lambda times frequency. Frequency is equal to speed over lambda. We know the speed because it's a light wave, 3 times 10 to the 8 meters per second, and we were given the wavelength. Now, wavelengths are often given in nanometers, so you always need to make sure you're doing your unit conversion. So you take 800 times 10 to the minus 9 meters, and so you get a frequency of 3.75 times 10 to the 14 hertz. Oh, and the kilohertz laser, it was a pulsed laser. It had nothing to do with the frequency of the light itself. The laser was, it was a nanosecond pulse laser, so femtosecond, oh my goodness. It was a femtosecond pulse laser, so that basically meant you had 1,000 pulses per second, and they were 42 femtoseconds in length. And you can do really cool things like focus them in gases and make plasmas, and then you can get blue light out of it, and then the blue light is related to the density of the gas that you're focusing in it, and it's so cool. So cool. Oh my gosh. Can't hype it up enough. All right, so there you go. There's our wave review over. We can move on to the next section. Which is the energy and momentum in radiation. So, if you recall back to last fall, chapter 8, which is our fun little chapter on, I can't even call it baby quantum mechanics. It's really like, here are a couple concepts which could eventually take you to quantum mechanics. We learned that photons have both energy and momentum. And then we saw this again in chapter 10 when we did collisions. And we saw how photons can play a role in particle physics. And they can give this to matter. So actually, to be honest, I actually think chapter 10 does a better job of really explaining how photons interact with matter. But we introduced the idea in chapter 8. So classically speaking, electromagnetic radiation also has both, that would be a both, no, it's not Hoth, the planet Hoth. Also has both transferable momentum and energy. Okay, so we are going to analyze how a charge on a spring reacts to electromagnetic radiation. So the spring model comes in handy a lot. And so there's a reason why we introduce it so early. Okay, so springs, we know that you can do this to them, that. Okay. I always keep a spring handy when I do these lectures. It's coming, I've used it a lot now for both classes. Okay, so let's say we've got our spring. There it is. Put a little charge on the end of it. I think it's a minus Q. We'll see if I stay consistent with that. So it starts at rest. All right, and now let's say we've got a little pulse coming in. So I am just going to put them all in the same color. No pulse. That, of course, is more like that. There we go. All right, so there's the pulse. And so it's at rest right now. This is barreling towards it. And what's going to happen when the pulse reaches the system? Okay, so there's some information that we should acquire. So we need to know the size of the pulse, and we need to know something about the timing of the pulse, if it's traveling at C. So we'd need to confirm C. I mean, it's a pretty standard assumption with electromagnetic radiation. I mean, although you can work in a lab that looks at slow light. So they have slowed light down to as slow as 300 meters per second, which is pretty cool. All right. So let's kind of draw some pictures. They will be bad. Here's a pulse. So we'd want to look at the length of this pulse. So if L is equal to 60 centimeters, then the length of time that it would experience this pulse, so 0.6 meters, we're going to assume C, 3 times 10 to the 8 meters per second. Then it would experience this pulse for a total time of 2 nanoseconds. So during time T, our little Q will experience a force equal to QE, because it'll have a field for that 2 nanoseconds. And so now we've got a force. And you know what force is called? Momentum changes. So this gives our little charge ball downward momentum for 2 nanoseconds. And so we changed our momentum. Let's calculate it. Our change in momentum is delta P is equal to P minus 0 is equal to F. Delta T is equal to minus QE times L over C. So, and what we'll have from this is a really short interaction, leaving a lasting oscillation. So if you had a perfect spring, it would oscillate forever. But if you don't, you have oscillation until mechanical friction stops it. All right, so now let's just, for funsies, let's bring in more stuff that we've talked about. So the oscillating ball now has kinetic energy. And if you recall, and hopefully this is no surprise, energy is a conserved quantity. So the only source of energy is the electromagnetic pulse. So our change in K, so we would have, look at this, we're bringing in momentum principle, energy principle, electromagnetic radiation. It all comes together. It's great. Physics is a building subject. Like, it really builds. Delta K is equal to K minus 0 is equal to P squared over 2M is equal to minus Q EL over C, quantity squared, 1 over 2M, because remember we calculated our momentum prior. We're going to assume safely the V of the ball, the speed of the ball, is much less than C. So we don't have a relativistic spring going on, pretty reasonable. And we know radiative energy is proportional to E squared. And since the ball has gained energy, the pulse of radiation should have lost energy. You can't get something for nothing. Always true. Except for your salvation. That you get for nothing. Well, you have to ask for it. But then it's yours. All right, so we know how to relate energy to electromagnetic radiation through energy density. So now let's look at this in terms of energy density. So we have energy divided by volume is equal to 1/2 epsilon naught T squared plus 1/2 mu naught B squared joules per meter cubed. So in the case of electromagnetic radiation, E is equal to CB, which we've already shown. So energy per unit volume is equal to 1/2 epsilon naught E squared plus 1/2 1 over mu naught E over C quantity squared is equal to 1/2 epsilon naught E squared 1 plus 1 over mu naught epsilon naught C squared. And if you recall, mu naught epsilon naught is equal to 1 over C squared. So energy per unit volume is equal to epsilon naught E squared. So, and energy density which is in joules per meters cubed, is related to energy flux, joules per second per meters squared. So we're going to keep going, but we need to recall a few things first so we know where we're playing. So recall, flux requires a bound area. You got to know where you're playing. So okay. So you want to look at this to determine flux. So in delta T, a volume A, C delta T, of electromagnetic fields passes through A. So we've got this field coming through it. It's going to take some delta T. So energy passing through A in delta T is epsilon naught E squared AC delta T. So you get flux is equal to epsilon naught E squared C is equal to epsilon naught E B C squared is equal to 1 over mu naught EB. And you should prove this on your own. It's some really cute algebra. And the direction of propagation or energy flow is E cross B. So, if E is perpendicular to B, then E cross B is equal to EB. And that's, you can easily prove that to yourself by looking at a nice little cross product setup. And this leads us to the pointing vector. S vector. And so the magnitude is the rate of energy per meter squared. So watts per meter squared. The pointing vector is equal to 1 over mu naught E cross B. Remember, this is the same direction as the direction of propagation. And it will have units of watts per meter squared. There you go. All right, let's do an example. The intensity of the sun around Earth's orbit is approximately 1,400 watts per meter squared. So we want to know E, the magnitude of E. Energy flux is equal to epsilon naught E squared. Let me write that again. Epsilon naught E squared C. So E is equal to flux epsilon naught C is equal to 14 watts per meter squared over 8.85 times 10 to the minus 12 times 3 times 10 to the 8 meters per second. And so we get 726 volts per meter, which is actually pretty close to the flux we get from the sun all the time. All right, so going back to our charge on the spring, with its change in momentum, and we've got our little pulse. So we have looked at electric force, but not magnetic. So we know that our E field causes a downward delta P, or a downward momentum. So what direction will the magnetic force be in? So we know that we have minus Q minus V, So minus Q times minus V cross B as this is going downward. And so, looking at this, we see that the direction will be to the right. And you can either verify that with the right-hand rule, or you can verify that by looking at the cross product setup. So, and the ratio of magnetic and electric force is QV over 2, E over C over QE is equal to 1/2 V over C. Okay, so let's return to the idea of electromagnetic radiation having momentum. So we've talked about its energy, but we've not actually talked too much about its momentum. So we know E squared is equal to PC quantity squared plus MC squared squared, energy. And we know that a photon has E is equal to PC. Because if this is 0, then these two are equal to each other. So momentum flux S over C is equal to 1 over mu naught C E cross B Newton meters squared. So, one more thought for this lecture, or this part of this lecture. If electromagnetic radiation gives momentum to a particle, electromagnetic radiation will lose that amount of momentum, which implies a smaller E field. And what we see from this is that when radiation hits matter, which happens all the time, protons and electrons experience radiation pressure. All right, we will stop here, and I'll see you next time.